So I hope you had a good lunch. We are going to have a whole jam-packed afternoon of sessions, starting with Quinn Dunki, who's going to tell us about Sprite compiling for Apple Hi-Res.
Hello. Can everybody hear me okay? Okay.
Yeah. Try now.
How about now? Am I dynamic and exciting yet? I need electronic amplification to be so.
We are not.
Oh my gosh, it's like an episode of Open Apple.
Yeah. Hello and welcome to Open Apple. This is episode 1 for KansasFest 2017.
Honors on standby.
Oh, no, this switch,
That's the most common thing.
Martin,
Oh.
Martin, the thing right
No,
there, I'm
no.
going to shut that off for some reason.
Shut this
I don't know why.
How about now?
Yeah.
Oh.
Hey, hello and welcome to Open Apple. Alright. Now I'm dynamic and exciting. Just needed this pile of electronics. Alright, so I'm here to talk about high-res Sprite compiling. And to start with, I'm going to talk about high-res graphics in general, a little primer on that. I am far from an expert on this. There are people in this room who know way more about it than I do, but this is what I spent my year learning because I thought it was really interesting. And I'm on roughly a 1 project per year schedule for KansasFest. So let's dive into high-res graphics. Now, many of you know or have heard through the grapevine or are familiar with it. It is kind of terrible. But in our defense, the year was 1977. And think about what the competition was at the time for computers that you could buy and own in your home. You had the Altair 8800, which had no graphics. You had the Apple I, which had no graphics. You had the Commodore PET, which had a form of character graphics, but the graphics screen was not pixel addressable. And then you had the TRS-80, which had pixel addressable graphics at a very crappy resolution and was black and white only. So that was the playing field. So let me get through this and so the point of all this is to frame the Apple high-res graphics in your mind as it was amazing that it existed at all, okay? Because it was high-res, pixel addressable, and color. And for 1977, that was pretty amazing. So in that sense, put into historical context, the Apple II high-res page was a really amazing thing. A lot of people bought the machine exactly for this feature, and that is probably the last nice thing I will say about Apple high-res graphics. All right, so it starts out pretty simple. High-res 101, you've got your memory map here. You've got high-res page 1 at 2,000 hex, high-res page 2, 4,000 hex. Simple. There's 2 pages. They are 8K each, which is 40 bytes per line. If you do the math, that is 192 lines. If you do the math again, you find there are 512 bytes unused. That's okay. So there's 192 lines, but note that I didn't say anything about horizontal resolution. And we'll get into why that is later. So one thing to remember is that digital computers create graphics modes by mapping binary to analog video signals. And analog video has no horizontal resolution, right? The horizontal portion is an analog signal. So everything in the horizontal direction is arbitrary. And in this case, extremely arbitrary. So let's start simple. Let's look at the top left corner of your high-res page in monochrome. So you've got a monochrome monitor connected to your Apple II, or you've got your Virtual 2 set in monochrome mode. The first byte looks like this. Your first bit is unused-ish, we'll get to that. And the next 7 bits are pixels, 1 bit per pixel. Great, except 7 pixels per byte, which is super annoying. Because guess what the 6502 is really bad at? Dividing by 7. So we're gonna get to that. The interesting takeaway here, though, is that Apple II high-res is technically a monochrome video signal. The only color that we get out of it is from NTSC artifacts, and it's actually called artifact color. So it's basically noise in the NTSC signal that, when created in a very specific way, creates the perception of color because of the details of how NTSC works, which we'll get into a little bit. But the other interesting aspect of this is that the interpretation of these bits to pixels is done by the monitor, right? Not the computer, which is very different from other types of 8-bit machines that have better graphics modes. So that's why you get different effects if you plug in a monochrome monitor or a color one. You get effectively higher resolution with a monochrome monitor because it's interpreting that video signal differently. And this is all a function of the fact that the high-res graphics video signal generator is very low level and very closely tied to the analog circuitry. All right, so.
So that means you need an Apple monitor.
Not really. So the high bit, as I said, is unused-ish. What it actually does in monochrome is acts as a half pixel shift, so which is a weird effect. Normally, you'd probably just set it or shut it off all the time in monochrome. If you mess with it, you can theoretically get a higher resolution. So with this normal monochrome usage, you get a nominal resolution horizontally of 280 pixels. With that half pixel shift, you can theoretically get 560. It's not really practical because all of the pixels within the same byte get the same shift. So it's not really 560 individual addressable horizontal pixels, but anyway, you can do some stunts. So try this if you happen to have a laptop in front of you, if you happen to have an Apple II emulator open. If not, then just look at your neighbors and imagine how much fun you'd be having if you had an Apple II emulator in front of you. Apple Basic, HDR, call -151, 2000:FF. What that did is put some white pixels in the upper left-hand corner of your screen, right? That is immensely satisfying and makes perfect sense. First byte is those 7 pixels that we talked about, right? We just set them all to 1, which is on, which is white. That is the last such thing you will encounter in Apple High-Res that is both sensible and satisfying. Now we're going down the rabbit hole. So that was byte 0 if we're in monochrome. Now let's plug in a color monitor to our Apple II and look at byte 0 and see what happens. Now we get more or less 2 bits per pixel and more or less 6 colors. So your high bit now becomes a palette bit, and I put that in scare quotes because it's not really what it's doing. But in the letters there, I'm showing how those bits now map to the first 3.5 pixels on the horizontal row. So there are 3.5 pixels per byte. And we'll see why that is in a little bit. You'll also notice I have written this in Canadian. Feel free to watch my slides for sight gags as we go along. We'll distract you from the tedious content on the slides themselves. So these are the high-res colors that we all know and love. Of course, green, magenta, blue, orange. There are 2 blacks and 2 whites, as many of you know, which is strange. And they're not even the same. They actually fringe differently, the 2 blacks and the 2 whites. So the first thing you might have always wondered is why these 4 colors? So what those 2 bits are doing in each pixel is modulating the, so if you plug in a color monitor, the color burst signal is now being listened to. So it's going to start interpreting this as a color NTSC signal, and these 2 bits are modulating the color subcarrier of the NTSC signal, and the so-called palette bit is shifting the subcarrier 90 degrees. So it gets a little deep into the analog electrical engineering there, but the point is that these 4 colors are all orthogonal phase shifts in the color subcarrier of the NTSC. So WAS is effectively bit banging the NTSC signal here, and that's why these bits directly control and act the way they do. So the blue and orange comes from when you shift that signal half a pixel and the color burst is enabled, then you get that color shift. So the artifacts change color, and that's how you get those 4 particular colors. So the reason that there's 2 bits per pixel, and the reason that works out that way, and the reason that there's 2 different sets of pixels is that the Apple II's clock cycle is 7/2 times the NTSC carrier frequency. And that was done intentionally because then it was really easy for WAS to do this bit banging video thing. So it allowed him to generate high-res video, which nobody else had, remember, without any kind of graphics chip. So that 7/2 is why we have 3.5 pixels per byte, because it's 7/2 of the frequency. So why is this also terrible? Again, because it's, people say, oh, the Apple high-res graphics is so terribly designed. Well, it's not designed at all. That's the point, right? So you look at something like the Commodore with its custom graphics chip, and it's got sprites, and it's got scanline interrupts, and some engineer sat down and said, I want a video mode. This is how I think it should work. The Apple II high-res is more like an emergent property of NTSC video hardware. It's not a designed mode at all. It just kind of happens when you jam bits at the NTSC carrier wave generator. So that's why we get all this weirdness. Again, amazing that it existed at all. All right, so that's byte 0. So far, so easy, right? Piece of cake. Now let's look at byte 1. So the byte next to it, still on the first row. Byte 1 in color now looks like this. So it looks very much like byte 0, except you notice that it is reversed. So odd numbered columns, the bits are reversed. So at the end of byte 0, we had half of pixel D, and then in byte 1, that half of pixel D is in the same place, and now it counts that way for the next 3 pixels. Okay, so every other column, the bytes are reversed, which is sort of a convenience because it keeps the bits of D together. But it's, again, not designed that way. It's just that's how the hardware, that's how the chips landed in the hardware. Pardon the pun. So again, 7/2, 3.5 pixels per byte. Okay, so that's bytes 0 and 1. So it basically continues like that across the entire row. So row 0 of your high-res page looks like this, going from 2000 to 2027. That's 40 bytes per row, 3.5 pixels per byte, which gives you effectively 140 color pixels per row. So this is the easiest way to think about Apple II high-res, is it's 140 color pixels across 2 bytes per pixel. As I say, there are other ways to interpret that data, the 560 trick, the monochrome thing, there are others, but this is by far the easiest way to think about it. Okay, so row 0, 2000, ending at 2027, right? Row 1, starting at 2400. Wait, what? Yeah, that's right. So the vertical now is also a mess. So row 1 starts 1K down from row 0. So every subsequent row is 1K below the row above it, and then it wraps around as needed. So again, row 0 ended at 2027. 2028 is actually line 8. Okay, so that's why when you see high-res images load, you get that Venetian blinds effect, right? That's why. If you load an image linearly into high-res memory, it jumps around effectively. And again, that was to do with saving chips in the address generator for the video scanner. Okay, so we think we have our heads around this. Now, if we want to actually write a general purpose pixel plotting routine, how do we do that? So effectively what we need to do for given pixel xy, we need to calculate an offset from 2000, the start of our graphics page. First thing we're going to do is find the row start, which is done very simply with this simple equation. Y modulus 8 times 1024 modulus 8k plus y over 8 modulus 2 times 128. That may or may not be right, but it's close. Got your row start. Then you need to find your horizontal byte within which your pixel lies. So that's easy enough, just x divided by 2 divided by 7, no problem. Write a divide by 7 routine, 6502, no problem. And then within that byte, now we need to find which bit is our pixel, right? Or actually which pair of bits if you're doing color. So to do that, you just need to know whether it's odd column or even column, the byte number, and then either you're going to do x over 2 mod 7 plus 1, or you're going to do 7 minus x over 2 mod 7 plus 1. Piece of cake, right? As you've probably figured out by now, nobody does that. So this is what people actually do. So I'll leave a little bit of wisdom. David Wheeler, I believe it was, who said, all problems in computer science can be solved by another level of indirection, which is what we do a lot on the Apple II. The great irony is that we created these machines for doing math really fast, and then we try really hard to never do math on them. Because math's actually super expensive. So yeah, this is what you typically do is you create lookup tables for the start of each high-res row, lookup tables for divide by 7, lookup table for mod 7. So that's how most high-res pixel rendering works. You have a set of lookup tables, and then it's actually pretty quick. So you end up with a row lookup function, something like this, where you pass in some sort of get address function where you give it a y coordinate that tells you what memory address that row starts. And then you find your horizontal byte the same way using the lookup tables. So we still have the problem, though, of setting pixels within a byte. That's still pretty expensive. You have to do a lot of ORing and ANDing and masking and stuff to set pixels within the byte. And if we're trying to draw like a spaceship that has a whole row of pixels, those pixels are going to be spanning multiple bytes, and then it gets even messier. So typically, the way games solve that problem is by pre-calculating shifts. So you have your little alien or your spaceship or whatever. You have 7 copies of that image in memory at each of the different 7 positions, and then you just pick the byte you want to start on, and then you pick the shifted image that you need to get the sub-byte alignment to get the exact right pixel you want, and Bob's your uncle. So that image is stolen from Apple Graphics and Arcade Game Design. One thing to note about this technique is there are issues with the high bit. So the problem with this pre-calculated shift method is that you're forced to assume the high bit value if you want to still avoid bit operations. So that means your sprite has to have the same high bit as your background, because otherwise when you or these images into your high-res page, you're going to be changing the high bit, and it's going to change the color of your background or create other weird problems. So if you ever wondered why all Apple II games have a black background, that's why. Non-black backgrounds are extremely non-trivial and often impossible. There are some special cases like Aquatron did this, where there was a black area and a blue area for underwater, and so they had a version with the high bit set for all blue background that they used when you went underwater. So there are ways around it, but like a complex background with different high bit values, that you're asking for trouble there. So putting all this together, then we end up with this sort of data-driven sprite rendering approach, which is again taken from this routine is taken from Arcade Graphics and Game Design, that book that I just mentioned, and this is very typical of how it's done. You have those sprite shifts sitting in memory somewhere. You use that lookup routine I showed earlier to get the start of your high-res row, and then you use this code to copy your bytes from the shifted image into the high-res page. And once again, Bob's your uncle. So the trick here is we would like our rendering and animation to be smooth. And the canonical way to do that is by doing all of your drawing inside the vertical blank, right? The vertical blank on the Apple II is 4,550 cycles. And if we're doing an 8x8 sprite with all of the shifts, remember you have to have padding at the end of your sprite to make room for all of the shifts that you need. So that comes out to 6 bytes wide for an 8x8 sprite. So this routine on an 8-byte wide or 6-byte wide sprite is 1,656 cycles. So that's about 2 sprite renders per vertical blank that you get, which is not very much. And if you're drawing sprites on top of other things and you want to move them around, you have to restore your backgrounds as you move, so that costs you an extra sprite render. So now you're really only talking about 1 sprite per vertical blank, which again is not very much. So typically you don't use the vertical blank because that's just not enough time to do anything with this standard data-driven approach. So let's do a little demo here and see what that looks like. Asking for punishment here, messing with video modes. So I do not have real hardware to show on because I traveled light. Okay, so this is a little alien dude rendering with that standard approach that I showed. There's all four colors are used in the sprite just to kind of make the point. And this is what happens, right? If you don't synchronize the vertical blank, which we can't because we're drawing and erasing 4 guys, right? So this is 8 sprite renders that we're doing right here. You get flicker, and we've all seen this in Apple II games. They're flickery, but he does look pretty sharp. He's got his green pants on. He's ready to play. Okay, so back here now. Really didn't think through this whole video modes thing. Okay. Oh. Bear with me here while I do this. Okay. So that flickering, the other thing I want to show you is, so that flickering effect, while it's tolerable when those guys are sitting still, in fact, I'll bring that up again. So the other thing I want to point out here is that these guys are rendering at row 0. So that means they have as little time as possible to render, right? Because your vertical blank starts here, and so you've got 4,550 cycles until here. So anything drawing at the top of the screen is the hardest possible case, right? So this is where we want to draw stuff to see how good our renderer is. So, you know, it's flickery, but maybe you could live with that. But the problem is the effect is magnified if anything is moving. So when we start, and these guys aren't moving very fast. The problem is, you know, during one of their little flickers, they might move 4 or 5 frames, right? Because we're rendering, you know, 8 of them. So you might miss, you know, these guys are only moving 1 pixel at a time, believe it or not. But because you're missing potentially 8 moves in the worst case per flicker, it just becomes unintelligible. So these are the problems we need to solve. All right, so what are the ways around that? So the first way around that, of course, is just flicker. Just let it flicker. Lots of games do this. If you're not doing a lot of diagonal cross-screen motion like I was showing there, you can get away with some flicker. So maybe for some of your sprites, you let them flicker, some you don't, whatever. Personally, I think this closely approximates poop, so I would prefer to just pretend that option doesn't exist. The second option is don't ever erase anything. This is lots of games do this, especially Space Invader style games where you're moving like a big grid of aliens. What you do is you just have a black border around the top and left side of your sprite, and then you just overdraw 1 pixel over every time, and you just erase as you go. And the nice thing about that is you're literally never erasing it, so there's no point during the video scan that thing is not rendered. So you'll get some tearing if it happens to render as the scan line passes over it, but you'll never get flicker. So that's a pretty good option for a lot of game types. Problem is your sprite velocity is limited. You're literally limited to how much margin you have around your sprites. And so if you want to move your sprites fast, let's say 4 pixels at a time, you need a 4 pixel border, but now that means you can't render your sprites close together because they're going to overwrite each other by 4 pixels. So you know, if things are passing over each other, which is a nice thing to do in games, you're going to get weird artifacts because of these black borders. So this trick really only works in very specific types of games, very specific types of sprites. Last thing we can do is page flipping, which is kind of what was probably envisioned, which is why there's 2 high-res pages. So the idea is you do all of your screen updates on a screen that is not visible, and then you flip a soft switch, probably during your vertical blank, and in one instant the page flips, and the video generator starts scanning the other memory region instantly, and so all of your updates were done invisibly. Your frame rate is still limited by how fast you can render in that background, but there won't be any flicker and there won't be any tearing. The downsides to page flipping is that it uses a lot of memory. That losing entire 8K just to double buffer your video is pretty expensive. And your sprite state gets really complex because if I'm rendering, I've got page 0 showing, I'm rendering back here in page 1. Now I flip my page and I render back here, right? Now I want to flip my page back again. I need to erase these guys. Their location is now 2 frames ago, right? So I have to store twice as much state for all of my game objects. So that's pretty expensive too. Your game logic gets expensive. As soon as you start double buffering your rendering, you have to double buffer most of your game state as well. Okay, especially if you're trying to do any kind of physics or animation, you got to double buffer all that state. So more complexity, more code. So what if we want to do better than all of that? How can we do it? So the next, so I went down this rabbit hole, got to roughly that point, and I started to think, well, how can we figure out what the actual maximum rendering speed of the Apple II is? How many pixels can we literally push before we can't push anymore? So what is the fastest possible rendering technique? Well, it's literally moving one constant byte to a place in video memory. A store instruction of a single byte to video memory is as fast as the Apple II can go, right? We know that for a fact. So it turns out that our fastest possible rendering technique is actually that thing that we did earlier. Storing that FF in the high-res page is the fastest way to render that white pixel, depending on how fast you type, I guess. But I don't recommend typing your sprites in real time. So this brings us to sprite compiling. Now, the idea behind sprite compiling is rather than a data-driven approach like we had with the arcade game graphics yada yada technique, we create code that just stores the sprites directly in memory. That's why they call it sprite compiling, because there's no data. You're not copying bytes around. You're just writing code that knows how to draw your sprites. That code sounds awful, right? So I think it was nicely summarized by KansasFest's own Marty. Hey, I can't write that code, or I don't want to write that code, but I can write code that can write that code. So let's think about what that would look like, that code, this mythical sprite compiled code. So let's say if I want to write an 8x8 sprite to one location on the screen, it takes 320 bytes worth of instructions to do that. That's not bad. But that's extremely specific code, right? It can literally, I want to draw my little alien dude, that can literally only draw that alien in one place. So that's not terribly useful. So let's say I want to generalize that to draw that alien on any of my high-res graphics locations that I have, that 280 by 192 resolution. Now I'm looking at 8.6 megabytes of code. That's a little less useful. So obviously we can't, that's not tenable. We've got 64K. We need some kind of compromise. So the balance we're trying to strike is between absolute speed, 8.6 megabytes, and absolute generalness, which is the data-driven approach, which was we only get to draw one sprite per vertical blank. So that's no fun. We need to be in the middle somewhere. So as I say, the fastest possible block of code that can draw a sprite into memory is a series of LDA constant store STA into video memory. That's the 8.6 megabyte option. The most flexible option is copying the sprite as data from RAM into anywhere in video memory. Then we got to do all the lookups to figure out where to draw it, yada yada. One sprite per vertical blank, and we're sad. I want to be sad. I want to have my cake, and I eat it too, because I like owning cake and I like eating cake. So, okay, so that brings us to HiSprite. HiSprite is a Python program that I played around with that takes an image from a PNG. So this is a PNG in GIMP of our little alien dude, looking very sharp. He's still got his green pants on, a little orange headband. He's got his purple antlers on. And it maps those colors to Apple high-res colors. And using Python code that looks something like this. This is a sort of the juicy bit from the middle. It takes that sprite data and it creates a stream of bits from the pixels, and it generates all of those shifts that we talked about, and then it writes, it spits out CA65 assembly code to draw all of those shifts in various places in the high-res page. So the generated code ends up looking something like this. So you've got, so Meg is the name of the sprite in this case. So there's an entry point here, figures out which shift you need based on your x coordinate you're trying to draw at, and then it jumps to one of the 7 shifts. And then each of the 7 shifts, it's calculating the row start, and then it's literally load, store, load, store, load, store for the entire sprite. So So this is a pretty good compromise. Your X and Y position are parameterized, but it's still just direct loads and stores of constants into video memory.
So that does one row.
Yes, yeah, I had to cut it off because the code is very long, as you can imagine. But yeah, any kind of Sprite compiler code, you run the tool and then you put it in a file somewhere and don't ever look at it because it's large and often unintelligible. So, okay. Again, we have to ask ourselves, what's the right level of parameterization? Here I opted to just parameterize X and Y position, but, to do that, I had to make some things fixed. Okay, I had which sprite I'm drawing is fixed. That's hard coded in these constants right here. This is that's the purple antler on my little dude. I had to fix the page number. If I wanted to also do page flipping, this will only store to high-res page 1. I could have parameterized that as well, perhaps, which gets a little messier. And every time we parameterize something, we gain a little flexibility and we lose a little speed. We also gain back some code size, so again, we're fighting that 8.6 megabyte ideal. But there are other options, maybe if you wanted even more speed, you could parameterize maybe just the row or just the column. So maybe you have this entire function here, maybe you have 192 copies of this for every row. Obviously that's, again, going to get pretty large, but it's an option to think about if you need more speed than this. This is the compromise that people generally land on with Sprite compiling, but it's not the only possible one. So demo time. But first, so this code is, so remember the data-driven approach was 1,656 cycles per sprite with the ability to draw anywhere on the screen. This still has the ability to draw anywhere on the screen and is 497 cycles. So that gives us 8 sprites per vertical blank. So now we're in the range of usability, right? 1 sprite per vertical blank is sad programmer. 8 sprites per vertical blank, maybe happy programmer. So let's see what that looks like. If my demo gods will cooperate. All right, so this is the same as demo 0. We were drawing 4 guys at row 0, again, the hardest possible place to draw. With our Sprite compiler, so as you can see, no flicker. So these guys are being drawn and erased every single frame, okay? So 0 flicker because we're getting it all done in the vertical blank period. So rock solid, 8 sprite renders, that's 4 sprites and 4 erases. Not too bad. And the nice thing is that now when we want to move them all over the screen, now they're perfectly smooth. And you can see that they overlap each other, they pass through each other with no weird artifacts, no messiness. So we can treat these as full-blown sprites and draw them anywhere we want, overlap them anywhere we want, don't have to worry about restoring backgrounds or anything like that. So that's kind of nifty, I thought.
How much memory per sprite does that approach?
That's a great question. We are going to get there, sir.
I feel like it might not be a great answer.
So, perfectly timed. Your check is in the mail, sir. Is it worthwhile? Is the $64,000 question. Probably not. The reason being, so you saw that one function there. I only showed you a tiny piece of it. It's about 2K of code for that sprite. So it's probably not useful for anything real, unfortunately. But it was fun, and the result is very pleasing. It might be useful in some special case, maybe for your player or spaceship or something, you want it to be extra smooth. If you have one particular sprite that's fast moving, something like that, it might be useful. It's hard to make the case, except maybe in the simplest game, where 2K of code for a single sprite would be worth your time. But, it's a neat stunt. So the reason this isn't very useful on the 8 bits is that, and the reason nobody did this, is that the video memory density to RAM ratio on the 8-bit is not favorable, right? We have a very high-res screen, a lot of pixels, and very little RAM. That's a bad combination. So we can't really afford the size-speed trade-off for something as extreme as sprite compiling. On the 2GS, however, sprite compiling is very effective and very popular, and in fact was how all the good games were done. Because on the 2GS, you've got not that many more pixels, but a whole lot more RAM. 4, 8, 16 times more RAM. So now all of a sudden this technique makes a whole ton of sense. So plus, on the 2GS, pushing pixels is your main, boundary to speed. On the 8-bits, it's less so. Like, even with all the complicated, pixel math you have to do, the lookup tables and stuff, it's all pretty quick. Like, you can do those indirect lookups for a couple of clock cycles. It's really not that expensive compared to all the, the 1 megahertz bus penalty and all that stuff you pay for on the 2GS. Writing to video memory is not necessarily your bottleneck. So, again, the trade-offs just kind of don't work out in your favor. So, yeah, probably not worth your time. But if you want to play with this, it's all on GitHub. There is a code for you to scan at your leisure. What's up there is the complete Python script that generates this code. Again, it takes a PNG file and spits out a large block of code that will render that sprite anywhere on the screen. Again, it calculates all the shifts and does all that jazz for you. So this took a lot less time than I thought it would, so I have plenty of time for questions. Yes?
You said on the odd numbered columns on the high-res screen, bits are reversed. So where does that take place? I mean, the scan line just goes linearly across. The memory is presumably linear. What's flipping the bits?
They flip because of how the video scanner works. So, I can't tell you the exact reason without looking at the schematics, but it's because there's a set of flip-flops that's scanning, that's generating the address values in the video scanner, and it's easier to let it bounce back and forth than it is to try and wrap it or reset it all the time. So
It wasn't on purpose, it's another consequence.
It saved a chip, yeah, that's why it's done that way. So as the video scanner is going across, generating the addresses, this set of flip-flops is just oscillating back and forth, and so that's why every other byte ends up reversed. That's the order that it's scanning memory in. Yeah. Kevin?
Kind of lost me at it was too expensive, 2K per sprite. And if you had, so you got a bunch of sprites, like 10, 12K. So what? You got 64K. Why is that bad?
Well, you still need room for code, right? Yeah. I mean, yeah, like I say, it might be worth it in some cases, but most games are going to have a lot more than, a hand. You want as many sprites as you can. You need a lot of room for code. You need room for character data. You need room for backgrounds. Unless you want to start doing a lot of disk access, you want, some backgrounds in the memory as well. So, like 2K is a lot when you compare it to the data-driven method where a single sprite is like 16 bytes. It's a huge difference. And the fact that every really good arcade game, even not even counting RPGs, just good arcade games, we're all pretty pressed on RAM. It's safe to say that they wouldn't have been able to afford, a 10x increase in the size of their sprites. So yeah, 2K is a lot for one little alien dude. As sharply dressed as he is, don't get me wrong.
Is the precompiled restoring, if you have a complex background, how does the precompiled restore the background?
Yeah, so again, one of the advantages to the vertical blank method of drawing is that it saves you a lot of having to restore backgrounds. So the precompiler generates the precompiler generates the code to render the sprite and the code to render a black blob in the shape of your sprite. And so, assuming you're running a black background, which you probably are because you're running a game on the Apple II, so your background is black because you don't like pain, and so you can avoid pain by making your background black. That's all you need to restore your background. So again, because the power of vertical blank-based rendering is that you can just redraw everything every frame, and you never have to restore backgrounds. If you're going to start trying to batch your rendering or whatever, then you have to start caching your background and putting it back when you move things. But if you're not, if the only things that are passing through each other are other sprites, they're all rendered in the vertical blank, then you never have to restore anything. So it saves you rendering time.
Could you sort your sprites and race the gun on an Apple II, or is that just not a thing?
Probably. It would be probably close to whether it's worth it or not. Interesting effect. So one of the things that actually let me show you the output of the tool here since I have extra time. So the tool outputs, while it's generating the code, it also does it outputs the cost of the function for you. So let's see if I can put that down there. So over here on the right is on the left is the actual generated rendering function, and here's the entire thing, and at the very bottom it calculates the clock cycles for you. So the generator is keeping track of how much code it's producing and how much each line costs and so on. So the nice thing about this is you can do the math and figure out how much rendering time you get. So you could probably also calculate based on the Y position of the sprite, let's say, how much more time you have. It might be worth it. I'd have to look into that, but I just wanted to see how much I could render in the worst case, which is row 0. I don't know why it keeps going to sleep like that. But this at least gives you a look at the output of the tool. And while we're in here, so this here is the actual Python script that generates sprite data. It's pretty simple. I hope Mark Pilgrim is not out there because my Python would make him die inside. I'm not a Python programmer. I don't know what I'm doing, but it's pretty simple code. So anyone's welcome to mess with that if they want. I think Rob McMullen is already working on an Atari version based on this. So, any other questions? Yeah.
Well, just a quick comment. You talked about the craziness of the screen layout. One thing I found is interesting to think of it is it's really just the 1K text screen in the first 1K, and then the next 7 high-res scan lines are just 7 more copies of that layout. You calculate the text and offset for a given text line that all works out in high res.
Yeah.
And you go down 1K at a time into the sub-scan lines. And if you're doing something that's aligned on 8 pixel boundaries, you can save a bunch of code so you don't have to type it into a scan line.
Yeah.
For tile-based systems, or that's one reason a lot of applications, a lot of tile-based graphics is because you get that sort of pulls away to the economy of scale and you can generate code or your loops or whatever.
Yeah.
But that's all part of the compromises of trying to change your design to fit hardware.
Yeah, that's a great point. It's the same video scanner doing all the video modes, so there's a reason those sort of parallels exist. Yeah, it's literally scanning. It's the same scanner that runs through the text page, runs through the high-res page. It just does it 16 times or whatever, however that math works out. So yeah, it's a good observation. Any other questions?
Can you think of any other concessions you could have made in design, like something similar to, but not exactly, let's say, skipping every horizontal position that would have been able to cut down on that size cost?
Yeah, that's a great point. So definitely, if you didn't need as much generality, if you knew you were only ever going to render on even pixels or something, yeah, you could definitely probably have the cost of the code. Things moving 2 pixels at a time definitely looks a lot rougher. So I was kind of trying to see how smooth I could get it as well. But if you wanted to actually try and make it usable, if you skipped half your horizontals, that would save a lot of space, probably close to 50%. Even there, you're still at 1K per sprite, which is still a lot compared to the data-driven approach. So
I agree with that.
Yeah.
So that's a relative assumption. Because you made the point yourself that you may want to do that for certain sprites in your game.
Yeah.
Not others. Another thing I can think of is some sprites may only move horizontally and vertically, right? So that you can look at other options there.
yeah, I'm sold. This is the best idea ever, and everyone should definitely go use this right now.
Faster, always better.
Yeah.
I just had a comment to share about your point about the pain of trying to use a non-black background when dealing with sprites, animation, and so forth. And in the Oxford Chaos project, I didn't know any better, so I plowed ahead down that road anyway with some off-tile grid animated sprites and things like spell effects, lightning bolts, and so forth. And ultimately, by the time I realized what you said about how painful it is and why nobody else seemed to do it, was really deep in. And the artist came to save the day, and what we ended up doing was essentially solving it through art, so that when the distortions happen, clobbering in the high bit, it somehow still looked okay, and essentially it looks like just an extra magical flourish that's happening around the screen. So just trying to kind of hide that under the rug.
Yeah, no, that's a great point. Yeah, the best games were very smart about how they built their artwork, and you can see it over the life of Apple II games. Really, you see the evolution of the artists figuring out what they can and can't get away with. You start seeing, black borders around white objects, and you start seeing white objects that are always, at least 4 pixels thick, and things like that. And all those tricks just minimized high bit problems, made things look sharper, minimized fringe, all that sort of thing. And so, yeah, you really see the games get better and better looking and more interesting looking. The early games, your enemy would be all blue or all purple, and then your ship would be all white, and then later they got better and better at doing that kind of stuff. So you look at something like Star Blazer, where there's a lot of colors in every sprite, but the art is all very cleverly built to get around the limits. And on this guy too, so he looks very colorful, but each row has a given high bit value. So the first row, there's no 2 colors on the same row that have competing high bits. So that way I don't have to worry about being able to draw him on any pixel having high bit problems. So that's another trick that was common. Yeah.
I think this is implicit. So that's using vertical art, like this one.
I'm sorry, I'm having trouble hearing you back there.
That's using the vertical line, right?
Yes.
Okay, so
Oh, yeah, good question. So, yeah, I should have mentioned that at the time. So this is timed to the vertical blank, which on the 2E and 2C you can check. There's a soft switch that's set during the vertical blank. So the code to do that is just, you wait for that flag to go high, and then you wait for it to go low again to make sure you have the full vertical blank, make sure you're not in the middle of it. Wait for it to go high, wait for it to go low again, and then frantically start rendering. On the Apple II Plus and earlier, there is that bus noise technique. The floating bus thing that can be used to detect the vertical blank. I haven't personally tried that, so I don't know how well it works, but yeah, it's possible. But yeah, of course, for the Atari folks in the audience, there's no interrupts, so we have no way of easily timing things to the vertical blank. So this code is just busy waiting on it. After 1 frame of rendering, it just sits there and waits for the vertical blank again. It goes again. Other questions?
Sorry, you said that you would check a flag for the 2C, or I didn't think it supported that. I had to implement it through interrupts.
Yeah, no, this probably doesn't run on a 2C. I just used the 2E flag.
So it would have been much easier.
Yeah, the 2C does have the flag. I think it's reversed though. Is the problem?
No, it's reversed on the 2GS.
Oh, maybe that's it. Yeah, I don't know. This works on the 2E. That's all I tested.
It works.
Other questions? Going once? Yes.
the one is going to have one alien is going twice as some faster.
Yes.
I can't quite see. Have you strategically kept it from the highlight portion? That one could conceivably have a problem.
So this guy here that's cruising vertically?
Yeah, right.
So
Does purple ever line up with
that's a good question. I mean, it might be, yeah, it is, yes. If the green feet happen to line up with the, orange stripe on another guy, the high bit would get borked on that byte for a split second. But yeah,
I didn't see it there. I was wondering.
It would be too fast to notice it. But yeah, in theory not in theory, that's definitely happening. So yeah, but again, it's so brief you can't really even tell. I actually never even seen it. If I was really fast on the freeze button, I might be able to catch it. But
Does the emulator replicated that faithfully?
oh yeah, absolutely. Virtual 2 does, yeah. Yeah, there you go. So you can see all kinds of stuff getting borked up in here. You know, there's the high bit being wrong right there. This green pixel turned blue on one piece of that dude there. This got really lucky. The blue and orange lined up on these two rows, so that looked okay, and the purple lined up. But yeah, that's definitely gonna happen. And you know, there's a reason that the eyes are 2 pixels wide as well, right? Because even with all of these tricks, you still can't put like a single white pixel right next to a single blue pixel in certain columns, because then the whole pixel turns orange. You know, like there's still issues with that. So you still have to follow rules of good Apple art design, which include making white things 2 pixels wide and stuff like that. But just sort of to prove the point of the advantages of sprite compiling over some of the other techniques is that these guys are all moving at arbitrary velocities. Some are moving 2 or 3 pixels a frame without needing any kind of black borders or anything around them. So, yeah.
Does the 2K include the mask of the transparent area, or is it just ATST?
That is just the so that is just the rendering of the guy. So I consider rendering the guy one sprite and erasing the guy a second sprite, because it's drawing a second sprite that just happens to be all black pixels. So it's really 4K per usable dude. Yeah.
But you could share all of the erase code.
Yeah, exactly. There's only one copy of the black code, because it's all the same dude.
So the erase doesn't have to be an erase. It could be a Pac-Man open and a Pac-Man closed, and then.
Yes. The trick there is you have to make your art pipeline more robust, because what this code.
My art pipeline is robust.
I've always said that about you. That Kevin Savitz has a robust art pipeline.
Hey, no sexual talk, okay?
So one of the tricks that this code is doing to get that 497 cycles per sprite is it's optimizing out. So it's optimized out 26 rows of that sprite, or 26 bytes of that sprite. And the way it's doing that is by detecting all black pixels. So that's what these increments are with no rendering. On this, like each of these groups is a single row of the sprite. So anywhere within this shift, if there's just solid black, it just skips those, and that's huge savings there. What that means though is you can't have. It means your black is your chroma key now, effectively. So if you want to also allow some black rendering, you have to create a mask and then have the tool be smart enough to match up, and allow some black pixels to come through and some not. And that was way more work than I wanted to get into. I just wanted to know if this was even practical to attempt. So.
Is there a reason that your sprites are not using the entire area of the high-res screen? It only looks like they go down so far.
Yes, because 16-bit math is a pain in the ass. That's why. Yeah, again, for this quick demo, I just wanted them bouncing around, so they just bounce around in the 8-bit math area, or as we call it, the rookie zone.
Everybody did that. Like all professional games did that too. You'd have like your scores on the right side,
Yeah, that's why you look at like Sea Dragon is a great example. There's a very elaborate animated dragon on one side and a big scoreboard thing on the bottom, and that's why, is to keep all the motion in the 8-bit zone. Yeah. Yes.
So this is out of scope of your talk, but
nothing's out of scope of my talk.
Oh, okay.
I got like 15 minutes to kill.
Okay.
So.
Well, so for double high res, okay, like every other byte is shifted between main memory and auxiliary memory.
So
to render, and if you want to render fast, would you render like? I don't know maybe if you looked at how other people do this, but if you rendered logically, you would shift all the switches between main and aux, and that would be slower.
Yeah,
but
so
if you like half your guy and then the other half.
Double high res is actually the techniques are actually the same. You just have to do everything twice. So the memory layout is the same, except every other column is in the aux memory page. The high bit gets ignored, and it's basically 4-bit true color at that point. It's 4 bits per pixel. So yeah, that's generally what you do is you render one row per page, and then you flip the page and render the other row, and you're effectively rendering every other column. So if you're doing a data-driven approach, you organize your sprites so that the sprite data is already interleaved, or a Sprite compiling approach, which might also be good for double high res. The code would be smart enough to be written that way. The challenge with double high res is, again, this can all be handled with tables and arranging your data cleverly, but even though the high bit is not used and it sounds great, 4 bits per pixel, those 4 bits it's still only 7 bits used per byte. So you still get bytes, still get pixels split across bytes, but now it's even worse because now half of every third and half pixel is in the other bank. So like pixel 0, 1, 2, pixel 4 is half in one byte, half in the other byte next to it, and those bytes are in different memory banks. So again, that you're sort of immune to all that if you just arrange your data so that it's pre-interleaved, but it's a lot more expensive to render that way. The nice thing though is that double high res does have 2 pages, so page flipping becomes a pretty good idea in double high res.
I know you're interested in the mouse also, and I don't seem to recall that mouse paint on the 2C had, it's not fast animation. I don't remember having flicker issues or weird line draw color issues. Do you recall, was that like a better version of high-res stuff when they did that? Did they just have some good tricks they used?
So, well, nothing is erasing, first of all, so that's the main thing. The mouse pointer, you just restore your background and draw it again. So that's easy enough. Nothing else on the screen is erasing. And it definitely had all of the artifacting issues. Most people used it with a monochrome monitor on their 2C, so you don't see it. Again, in monochrome, the high-res screen looks so much nicer. But, if you flipped on a color monitor, mouse paint looks like garbage. It really does, because it was written with monochrome in mind. Yeah. Any other questions? Probably have time for 1 or 2 more. Yeah.
I apologize, I don't want to make them out of me, but I wanted to say that a lot of these techniques were applicable for flappy burn and double low res. They used a mix of sprites with borders. The pipes have blue background of the sky behind them. It used sprite compilation for the burn, and it also used what you talk about, which is chasing the beam, so I actually wait for it to go past me. And then I start doing my work behind it, which required a very specific pipeline that was okay because the game style was very dictated. So I apologize for interjecting.
Cool, yeah.
These things are applicable across a lot of the different graphics modes.
And it does raise the point that all the best games used a mix of all these techniques, depending on the game type, depending on the particular screen element within the game. Again, your Space Invaders game might be using the black trailing technique for the aliens, might be using a different technique for the ship, a different technique for the bases. So, you got to mix it all. That's why there's no generic sprite libraries for the Apple II, right? Because every piece of every game has to be done in a very specific way that's the best for that exact application. Yeah, maybe time for one more? No? All right, thanks everybody.